Now, I said this in a previous video, but you can always find all this stuff just by looking at a graph. The issue is it's not as accurate, and we might not always know what those values are. But in this video, the thing I want to focus on is what we call an inflection point. I've mentioned this term already, and let's go ahead and define it. And basically, how I remember it is it's essentially the same thing as a critical value for the second derivative. So a critical value is when the first derivative has a value of 0 or is undefined. So for the second derivative, an inflection point occurs when the value either is 0 or the second derivative is undefined, either case. And basically, it's going to be indicating a change in concavity. So let's actually look at the graph from our previous two examples. So in the last video, we examined function g and h, where we determined the mins and maxes by using the second derivative test and examining everything we knew about them. And if you're looking at a graph, you can always figure out approximately where your critical values and your inflection points are just by looking. Like, critical values are easier because that happens at the top or bottom of a hill. Like, critical values should be there, critical values should be here. And on H, we should have a critical value here. We should have a critical value there. And also, one that might be a little bit easier to miss would be at this location, because critical values occur when the first derivative is 0 or undefined. And notice that it does appear to be flattening out approximately right about there, where it basically anywhere it levels off, you can imagine it being flat, having a flat tangent. That's a critical value. And if we go back to the math, notice that that's consistent. Hopefully, we had -3 and 1 for g of x, which is this graph here, -3 and 1. And for h of x, we had 0, -3, and 3. So 0, -3, and 3, all the way consistent. So what's an inflection point? An inflection point is where, like I described before, it changes in concavity. Like examining g, notice it appears to be concave down here. Like, looks like an upside down parabola. And over here, it appears to be concave up, kind of have that upward U shape instead of downward. It's got to change somewhere in the middle. And we, a question would be, well, where is that going to be? Just by eyeballing it, it could be, somewhere in between. But basically, it's going to be where the slope changes from being decreasing to increasing, or vice versa, from increasing to decreasing. It sort of has like a bendy look to it. And that sort of bend, change in direction is another good way of visualizing it. Like, if you imagine that the curve is imagine this is you driving your car. Like, here you're making a sharp right turn. Like, imagine you're in Fast and Furious and you go like screeching around the corner there. All of a sudden you switch from turning to the right to the left. That's an inflection point, is where you're changing direction. Notice a critical value, you're not actually changing your curvature. You're changing from going up to down. It's sort of like imagining a roller coaster, tops and bottoms, but it's sort of like a different idea. Change in directionality. Imagine driving your car. Like here, notice here I'm driving, making a sharp right turn. And then again, another way of visualizing it is here, concave down. Notice this part of the curve appears to have that concave up. It doesn't have to be a full U to be concave up. It just has to have the gradual change. So somewhere about over here, I can imagine there's an inflection point because it's switching from concave down, to concave up. Now at this point here, it appears to be concave down. So I'd imagine that there's an inflection point probably at the same location as the critical value. Usually inflection points are not the same as critical points, but sometimes they do line up. And now I'd say this is concave down. And again, notice over here, it's concave up. So again, there's probably another change in concavity over here. And again, if I'm imagining driving my car here, I'm making a right turn. Now I'm turning to the left. Now I'm turning to the right. Now back to the left. And every kind of like change in direction is an inflection point, kind of like a twist, if that makes sense. But again, you can analyze all of these things mathematically. You don't have to just look at a graph. And if you're finding that kind of hard, you can always find an inflection point in the same exact way as a critical value, except for you're going to take the second derivative and set it equal to 0 instead. So let's go ahead and do that. And we've actually already found the second derivatives for each of these functions. G double prime of x was 2x plus 2. And h double prime of x was 20x cubed minus 90x. So refer back to the past couple videos if you want to double check that out. And basically, to find the inflection points, you just take the second derivative and set it equal to 0 in the same way we found critical points, except for that was for a first derivative. Now, to solve for the the inflection points for g, we just need to subtract 2 and divide by 2. And what we'd end up with is x is equal to -1 is our inflection point for g. And there's only one. And looking at it, consistent, appears to be right on target for where we guesstimated just by looking at it. And now with h of x, same deal. We would set the second derivative equal to 0 and solve. And here, this is a little harder because we have lots of terms, but notice that we have a common factor of 10x, and we often want to use factoring in order to solve these things, especially when we're dealing with polynomials. But basically, we factor out 10 from each, factor out x from each. That would leave us with 2x squared minus 9. And here we'd have an inflection point where whenever you have a common factor of x, 0 is going to be one inflection point location. And notice that's consistent with our critical point, which was at the location of 0 for h, which is this graph. And then we're also going to have inflection points somewhere else along in between on the left-hand side and the right-hand side. And that should correspond with the solutions here. Now, 2x squared minus 9 is not exactly a difference of squares, so we can't perfectly factor that. But we could always set it to 0 and figure this one out as well by just writing an equation. So I could add 9 to both sides and then divide by 2. But basically, I would have x squared is equal to 9/2. That is not a perfect square. I could always take the square root here, which, remember, when you take the square root of x squared, it will always leave you with the square root. But it's going to give me about the square root of 9/2, or square root of 4.5. And that comes out to be, let's just estimate it as a decimal value, approximately plus or minus 2.1, and those would be the inflection points, the other two inflection points. And again, looking at our graph, notice it appeared that we had 3, about -2.1 and +2.1. Again, we weren't exactly sure, but if you want to find inflection points mathematically, you need to take the second derivative and set it to equal to 0.